In this video, I will introduce our new paper published on ECCV 2024 of GlobalPointer, Large-Scale Plane Adjustment with Biconvex Relaxation. First of all, I will introduce the background and motivation of our paper. With the widespread adoption of LiDAR technology in applications such as 3D reconstruction and LiDAR SLAM, tasks involving localization and scene modeling have gained significant attention. As a fundamental building block, there is an increasing demand for a more efficient, robust, and accurate multi-frame point cloud registration algorithm for downstream tasks. In this paper, we mainly focus on plane-based multi-frame point cloud registration, which takes multiple LiDAR scans and associated point-wise plane labels as input, simultaneously optimizes the LiDAR poses and plane parameters, finally outputs accurate LiDAR poses and planes reconstruction. As the core non-linear optimization component, plane adjustment simultaneously optimizes the LiDAR poses and plane parameters by minimizing point-to-plane or plane-to-plane errors. Prior state-of-the-art methods explore both non-linear least square methods and spectral-based methods to improve the performance of plane adjustment. While existing works on plane adjustment have shown promising results, these methods are limited to small-scale problems, and their accuracy depends on the quality of initialization. Our method is the first attempt to achieve both large-scale and globally optimal plane adjustment. In summary, our contributions are as follows. Firstly, we exploit a novel optimization strategy termed biconvex relaxation, which combines the advantages of both alternating minimization and convex relaxation techniques. Secondly, building on this novel optimization strategy, we develop two algorithmic variants for plane adjustment, namely GlobalPointer and GlobalPointer++, which depend on point-to-plane and plane-to-plane errors, respectively. Finally, extensive synthetic and real experimental evaluations demonstrate that our method can perform large-scale plane adjustment with linear time complexity and robustness to poor initialization, while achieving similar accuracy as prior methods. Next, I will derive our main contributions in details. Before formal derivation, let us recall the point-to-plane and plane-to-plane error. The point-to-plane error measure the projection distance between a point and a plane. Besides, the plane-to-plane error can be defined as the sum of direction distance and position distance. At the beginning, I will discuss our proposed algorithm, GlobalPointer. This algorithm begins with the point-to-plane error version plane adjustment. However, this problem is highly nonlinear and has non-convex objectives and constraints. This makes it hard to optimize. To solve such issue, we exploit a novel optimization strategy termed biconvex relaxation, which have three main sub-steps. 1. Decouple the original complex formulation into two sub-problems, namely plane-only and pose-only problems. 2. Reformulate each problem using convex relaxation technique. 3. Solve each problem alternately until the overall problem converges. We will firstly discuss the plane-only problem. Given the original plane adjustment problem, we can fix pose variables a t and only optimize plane variables. Then after some reformulation, we arrive the plane-only quadratically constrained quadratic program problem. Convex relaxation technique then can be used to relax this QCQP problem into the semi-definite programming problem. This SDP problem is now convex and can be solved in polynomial time with any off-the-shelf optimization solver. Similar to the plane-only problem, the same technique can be used to formulate the pose-only SDP. Once combining these two solvers, we immediately arrive a scalable and initialization-free algorithm named GlobalPointer. GlobalPointer alternately solves each problem until the overall problem converges. Apart from the GlobalPointer algorithm, we further propose a variant algorithm named GlobalPointer++, which measures registration quality by plane-to-plane error. Inspired by the biconvex relaxation technique, we can fix pose variables r, t and optimize plane variable. Due to the special structure of the problem, we can solve each plane variable analytically. Similar to the plane-only closed-form solver, we can derive the pose-only closed-form solver. Once combining these two solvers, we immediately arrive the accelerated plane adjustment algorithm variant named GlobalPointer++. GlobalPointer++ alternately solves each problem until the overall problem converges. Finally, I will show some experimental results. For synthetic dataset, we generate numerous virtual planes and virtual observation poses. Each pose is set to be inside a box with a maximum size of 50 meters, and each plane is set to be observed from any pose. We evaluate the runtime of GlobalPointer and GlobalPointer++. The number of planes and poses increases gradually, using well-initialized parameters. As illustrated, the runtime of GlobalPointer exhibits a linear growth trend with increasing numbers of planes and poses, while GlobalPointer++ achieves a 5-10x speedup compared to GlobalPointer. We extensively compare our proposed algorithms with other methods in terms of accuracy under varying levels of point cloud noise and pose initialization noise. We choose the total point-to-plane error as the evaluation metric. As shown in this figure, GlobalPointer consistently converges to the global optimum across all settings, while GlobalPointer++ is more sensitive to point cloud noise. We also evaluate the growth of time complexity for the algorithms. Starting with 5 planes and 5 poses, we incrementally increase the number of poses and planes. Time complexity is measured as the multiple of the optimization time relative to the initial setting. Experimental results in figure demonstrate that our two algorithms exhibit similar linear time complexity. For real datasets, we select sequences from the Hilti dataset with a higher number of indoor planes. In the figure above, we compare the accuracy of our algorithms with other methods. It is evident that our proposed GlobalPointer and GlobalPointer++ consistently demonstrate global convergence performance across all settings, while other methods require well-initialized values to converge to the ground truth. Thanks for watching.